The new topic is entitled Basis and Dimension. We'll start off by giving a definition of a basis. Some of you might have seen this definition coming. The vectors v1, v2 up to the n in a vector space V are said to form a basis for V if the following two conditions are met. If, on A and B, if V1 through Vn spans V and V1 through Vn are linearly independent. Like the smallest basis that you can come up with. The smallest basis you can come up with. Okay, we remove the dependent vectors from the spanning set. In other words, if in Vn I also had W1 through, in the spanning set, if I also had W1 through Wm, okay, it still spans V, because if you add more vectors to a spanning set, it still spans. We know that if V is in the set V, then V can be written as a linear combination of V1 through Vn, because that set V1 through Vn, it spans V. So now, if what I add on is the zero vector, then this whole mess will still will still equal V. And V is any vector in the vector space big V. So what I'm going to do is, I'm going to add on, call him D. 0. 0 W1 plus 0 times W2 all the way down to plus 0 Wm. So I just added on 0. I just added on a lot of 0 vectors. It doesn't do anything. The sum is still going to be whatever this mess was, which is little v. So I'm adding on the 0 vector, 0 times W1 all the way up to 0 times Wm. And if I remove the vectors that I don't need, these are extra vectors. That is, now this set of vectors is linearly independent. Oh, it's a basis. If you have a set of vectors that's a linearly independent set of vectors that also span V, then this set of vectors is called a basis for V. So some quick examples. The set of vectors that contains E1, 1, 0, and E2, which is 0, 1, is a basis for R2. Because the span of these two vectors is R2, and those two vectors are linearly independent. In general, the set E1, E2, up to En is a basis for Rn. Remember, E1 will be 1 and then a lot of zeros, N entries in all, and E2 would be 0 and then a 1 in their second position, and a lot of zeros, and eventually En will be a lot of zeros at the beginning, and the nth position will be a 1. These vectors span Rn and they're linearly independent. Hence, it's a basis for Rn. So, problems you're going to see are going to be of this type. You're going to be given a set of vectors and a vector space. Let me say it slightly different. You're going to be given a set of vectors in the vector space V. And you're going to be asked, does this set of vectors span the vector space V? Does this set of vectors span the vector space V? And are they linearly independent? That is, do they form a basis for this vector space V? Suppose you were asked to show that S, which contains these 4 vectors, show that S is a basis for R4, where, and I defined V1, V2, V3, and V sub 4. Where V1 is, I think with some good ones, 0, 1, 0, 1. V sub 2 is, say, -2 or +2, -1, 1, 0. V3 is 1, 2, 2, 0. And V4 is 1, 0, 0, 1. So we want to show that this set of 4 vectors is a basis for R4. So I want to show that it spans R4. So let A, B, C, D be an arbitrary vector in R4. I want to show that I can come up with a linear combination of V1 through V4 that gives me A, B, C, D. Okay? And I also want to show that, so let me just say this for a moment. This is for spanning R4. Okay. Now over here, I want to show that, just the way I'm writing it. Let me write it this way. I'm going to think of the nicest way to write this so everyone understands it. On the left side, we're going to do the spanning, and the right side, the linearly independent. Okay. So, let A, B, C, D be arbitrary in R4. Okay? So the question is, can I find 4 scalars? Can I find 4 scalars that when I do a linear combination of V1, V2, V3, V4 gives me ABCD. Gives me ABCD. Okay, now for linearly independent, something else I need for a basis, I want to show that that a linear combination. I'm going to use the same letters, C1, C2, etc. C1, V1. Let me write it up here. C1, V1 plus C2, V2 plus C3, V3 plus C4, V4. I want that to equal to 0, 0, 0, 0. Okay. And then I want to show that on the right, I want to show that all these C's have to be 0. And that will give me linearly independence. On the left side, I just want to be able to find those 4 C's so that the linear combination gives me A, B, C, D. Okay. Now we're going to try to tackle both of these at the same time. To solve this system of equations, I would solve this. V1 I put down as the first column, as we've done many times already. V2 in the second column. V3 in the third column. V4 in the last column. Okay. Now, let me just change, only because it'll look neater looking. Let me try to solve this system of equations. That just means I put this down. Okay? Now, if I want to solve this system of equations, then I augment it with A, B, C, and D. We're going to tackle both at the same time. When you reduce this, what you get is, and make sure you can do this, what you get is the 4x4 identity matrix augmented with, well, those zeros will never ever change. 0, 0, 0, 0, augmented with a mess. I got negative 4a minus 3b plus 5c plus 4d. Next entry was negative 2c minus 2b plus 3a plus 2b. And then I got a plus b minus c minus b. And for the last one, I got 4a plus 3b minus 5c minus 3b. Okay. First time through, just ignore the last column. Ignore this. So what we have is C1 equals 0, C2 equals 0, 0C1 plus 0C2 is 0, plus 1C3 is C3, plus 0C4 is C4 equals 0. I meant to say C3 equals 0. 0C1 plus 0C2 is 0, plus 1C3 is C3, plus 0C4 is C3, and that equals 0. The last row, for the same argument, C4 equals 0. Okay? Now, how about we just change these to D's? Let's change them to D's. So that first, this portion of the matrix implies that B1 equals B2 equals B3 equals B4 equals 0. They're all zeros. So that implies that the columns, let's give this matrix a name, call just up to the augmented line. Let's do this in a different color. This matrix right here, we're going to call it A. We call it A. This implies the columns of A, because we got it to be row equivalent to the identity matrix. The columns of A are linearly independent, which implies the column of A was just S. The column of A was S, V1, V2, V3, and V4. So that implies that S is a linearly independent set. So that's half of the job. The other half of the job, due to lack of space, is going to happen on the top. Okay? It's going to happen on top here. Erase this on top and move on. So we can handle both of these steps. Spanning and linearly independent with just one reduction of a matrix. We just augmented it twice. Okay, now we're going to ignore that column. We're going to ignore the homogeneous system. So now what we have is C1 is equal to this mess. And I'm correct when I call it C1. Okay, so C1 is equal to this first row. I'm not going to write it, please. And C2 is equal to that mess. And C3 is A plus B minus C minus B. And C4 is this. And they're all well defined for any A, B, C's, and D's. We're never dividing by 0. Okay? So this implies then on an exam, you better write down what C1, C2, C3, and C4 are. Again, here they are right here, the bottom right. This here is C1, that's C2, that's C3, and the last one is C4. Okay, well this implies that V is in the span of S. Well, S is linearly independent, and this implies that S spans V. So S spans V, and S is linearly independent. Therefore, S is our basis. Watch this 5, 10, 25 different times. Okay? And be really until you get it. You only have to watch it once. Wonderful. Myself, I had to watch it for 3 weeks straight. And then I'm like, oh, okay, this makes sense. The vectors really don't matter. It's just you have to reduce them. So basically, if I gave you any vectors in R4 or any other vector space, what you're going to do is you're going to put the first vector, you're going to put the second vector, and if you have more, you'll put the nth vector, and then you're going to augment it with the 0 vector, and then you're going to augment it with the right-hand side. And instead of using A, B, C, D, that was very favorable in R4, but in Rn, I'll use A1, A2, down to AN. Reduce this. If it turns out, and this first column will be C1, C2, and coefficient Cn. If it turns out that C1 must equal 0 and C2 must equal 0, in fact, all the C's, N's must equal 0, then it's linearly independent. And if you can solve C1 in terms of these, where it's always well defined, that is, you don't come that C1 is A1 minus 2A2s over A3. Because then A3 can't be 0. Okay? But that's not going to happen if you think about it. You're never dividing by anything. You're always adding multiples of one row to another. Okay. So this here is the recipe. You put in, so they give you a set S. S is equal to these vectors. You write the first vector as a column vector, the second one, the third one, the fourth one, the last one. And then augment it with, well, if you're in R5, well then certainly put down 5 zeros. And then put down A1, augment it again, A1, A2, all the way up to A5. And then solve for the C1s and the C2s. First solve this system without this last column. Okay? And then if all the C's have to be 0, then you have a linearly independent set, and you really should go on. And then find out what the C1s are with respect to this system of equations, the one that isn't homogeneous. Remember, A1 through AN is the arbitrary vector in the vector space, V. There was your recipe. You do that and you reduce it correctly, you'll never have any problems. Never ever have any problems. It just involves you reducing a matrix. Your teacher and or textbook may tell you to do 2 augmented matrices. One with the zeros and one with the arbitrary vector. No. Why do it twice? Just reduce the matrix once. Okay. Here's a nice problem. Give you 4 vectors in M22. Remember, M sub 2, 2 is the set of all 2 by 2 matrices with real entries. Show that S, which equals to this set of matrices. In this case, matrices are vectors. Write down the set first. Show that S is a basis for M22. Now, since you don't have regular vectors, you can't write down, oh, this is simple. Write down the first matrix for the first column, and then write down the second matrix for the second column. No. You can't do that. So what we're going to do is have to show this one by one. Actually, I can't do it in one step. I want to show that it's a linear combination of these four vectors, C1 times the first matrix plus C2 times the second matrix plus C3 times the third matrix plus C4 times the last matrix, if this is the zero matrix in M22. Does this imply that all the C's must be zero? C1, C2, C3, and C4 must be zero. Well, this here is just multiply each entry. That should be a zero down here, sorry. Multiply each entry in the matrix by C1. So C1 times 1 is C1, and then the others will be 0. Plus C2 times 0 is 0. C2 times 1 is C2. C2 times those zeros in the bottom are zeros. Plus C3 times 0, C3 times another 0, C3 times yet another 0. This C3 times 1 is C3. Plus C4 times those zeros are 0. C4 times 0 is still 0. C4 times 1 is C4. And it still equals the right-hand side. Now, what do you get for the 1, 1 position? What do you get when you add those four values? C1 plus 0 plus 0 plus 0. You get C1. For the 1, 2 position, 0 plus C2 is C2 plus 0 plus another 0 is just C2. 0 plus 0 plus C3 plus 0 is C3. The 2, 2 position, 0 plus 0 plus 0 is 0 plus C4 is C4, which tells me that this left-hand side of the equation is just what I wrote down. And it still equals to the right-hand side. And if two matrices are the same size and equal, identify the locations. C1 is 0, C2 is 0, C3 is 0, and C4 is 0. That is, they all equal one another, and they equal 0. But if all of the scalars, if all of these scalars have to be 0, the linear combination gives you the 0 matrix, and the scalars have to be 0, then you can say that implies that S is a linearly independent set. This set S at the very, very top, this set of vectors is linearly independent. So we are to proceed to show that it's the basis. If S is not linearly independent, that is, it's linearly dependent, we stop. We stop because it failed one of their major conditions. One of their two conditions failed. So now what we're going to do is we're going to show that the set spans M22. And part of this work we've already done, and we're going to use the results. So we need to pick an arbitrary matrix in M22. Let A, B, C, D be any matrix in M22. So I want to show that a linear combination of the vectors in S can give me A, B, C, D. Okay, so I want C1 times the first matrix in S plus C2 times the next matrix in S plus C3 times the third matrix in S plus C4 times the last matrix in S, and it's supposed to get me this arbitrary matrix. I commented a moment ago that we did part of this work. That is, we know exactly what this is. We already did it. It's C1, C2, C3, C4. And it equals the right-hand side, which is A, B, C, D. So this implies that C1 is A, C2 is B, C3 is C, and C4 is D. Well, this implies that S spans M22. The next and last line, combining what we've discovered. We discovered that S is linearly independent and S spans M22. Therefore, S is a basis for M22. In fact, it's the natural basis. It's the natural basis. Just let this be A, let this be B, let this be C, and let that be D. After all, that is what we discovered. It's very similar to E1, E2, E3, E4. It's a very fair problem on an exam. Now, here's a nice theorem for an exam. Hopefully, the linear algebra class, you have to do proofs on an exam. If S, which is V1 through Vn, is a basis for a vector space V, then every vector in V can be expressed as a linear combination of vectors in S in a unique way. And we know that if S is our basis for V, then S spans V. That is, any vector in V can be written as a linear combination of these vectors in S. But we're going a little bit further. We're saying if S is the basis, then that linear combination is unique. You can't write an arbitrary vector V in little v in the vector space V using two different linear combinations of the vectors in S. Let's prove that. Proof. Let V be in V. Since S is a basis for V, then S spans V. And that's one of the definitions for a basis. If S is the basis for V, then S spans V, and S is linearly independent. The vectors in S are linearly independent. S spans V. Okay. Now, then for each little v in V, V can be expressed as a linear combination of vectors in S. Now, suppose there's multiple ways of doing that. Suppose little v is C1V1 plus C2V2 all the way up to CNVN, and little v is D1V1 plus D2V2, etc. up to DNVN. Now, I want to show that these coefficients are equal. That is, they're not two different linear combinations. Let's subtract. Vector v minus vector v gives you the zero vector. The zero vector. On the right side, when we subtract, we get C1 minus B1 times V1 plus C2 minus D2 times V2 all the way down to Cn minus Dn times Vn. So let's see what we have. We have a linear combination of V1 through Vn that equals a zero vector. But wait a minute. V1 through Vn is the basis for V. But that means S is linearly independent. But S, being our basis for V, is a linearly independent set. I have a linear combination of V1 through Vn, which gives me the zero vector. And V1 through Vn is linearly independent. Oh, all those scalars have to be zero. All those scalars have to be zero. All the scalars are zero. So, C1 minus D1 equals 0. C2 minus D2 equals 0. All the way down to Cn minus Dn equals 0. When you subtract two quantities and you get 0, that means the two quantities are equal. Well, that implies C1 equals D1, and this being 0 implies that C2 must equal D2. Cn must equal Dn. And that's exactly what we wanted to show. We wanted to show that these two right sides are the same linear combination. Not only do they both equal vector b, but it's the same linear combination. We couldn't get two linear combinations, two different linear combinations. What this is saying is if v is equal to 3 times vector 1 plus 4 times vector 2 minus 3 times vector 3, etc. up to 104 times vector n, then v cannot ever equal to 4 times v1 minus 11v2 plus 4v3 plus, sure, this can be 104 vn. Once these are different, they can't be equal. It can't, this and this cannot give you v. A vector in a vector space, you have a vector in a vector space v, yes, and you have a basis S for this vector space. then a linear combination of, there are no two linear combinations, no two different linear combinations in this basis S that give you the same result. Okay, think about that for a while. This is hardball. You have to make connections. It isn't like you do the same to both sides. You add 7 to both sides of the equation. No. You have to understand it. Understanding it is a lot easier than memorizing it. Now, here's a very important theorem. I'll state the theorem and we'll talk about what it means. Let S be the set of vectors v1 through vn. Let it be a set of non-zero vectors in a vector space V. And let the span of S be called W. So the span of these vectors is just called W. Then some subset of S is a basis for W. You have the vector space V. You have the set S. Now, every vector in S is in the span of S. For example, if VI is in S, then why is VI in the span of S? So S has a lot of vectors, or maybe it doesn't have a lot. Why, if VI is in S, why does that imply that VI is in the span of S? Reason being is you can take 0 times V1 plus 0 times V2 all the way up to just 1 times VI, and then 0 times VI plus 1 all the way down to 0 times Vn. All of these are 0, the 0 vectors, what I just highlighted. And when you add the 0 vector to the 0 vector, you get the 0 vector. But this vector is just VI. The 0 vector plus VI plus 0 vector is VI. I can come up with a linear, so this vector, which is VI, this vector, which is VI, is in the span of S. Okay. So why did I say that? I'm not exactly sure why I wanted to make a big deal of it, but I just wanted to show where the span of S is, and little s is in it. Okay. Now, it might be that S is not linearly independent. It might be that S is not linearly independent. Okay, so what we can do is take our subset of S. Take our subset of S. Take these vectors, which two things I'll say about these vectors. They're linearly independent, and they also equal the span of S. They also equal the span of S. You can remove some of the vectors from a spanning set to form a basis. You can remove some of the vectors from a spanning set to make it a basis. That is, you're going to remove some vectors from S, and it's still going to span the same set, the same space, and the vectors will now be linearly independent. The vectors will be linearly independent. I'm not going to prove that one. It's not even a hard proof, but I'm not going to prove it. Let S equal V1, V2, V3, V4, and V5. Okay, let S be that. Let it be a set of vectors in R4. Where V1 is 1, 2, negative 2, 1, etc. V2 will call, I actually wrote these down, 3, 0, negative 4, 3. V3 is 2, 1, 1, negative 1. And V sub 4 is negative 3, 3, negative 9, 6. So I want to find a subset of S that is a basis for, that is a basis for the span of S, which I choose to call W as indifferent. Now, what you want to do is remove vectors from V that are dependent on the others. So what you do is the following. Now, you want to find out which scalars are not 0. Okay, you want to find out which scalars is not 0. Okay, which vectors are a linear combination of the others? Well, to solve this system that I wrote down, you write down vector 1 as the first column, vector 2 as the second column, vector 3 as the third column, vector 4 as the next column, and of course I didn't write down what vector 5 was. Nice of me. I forgot to write down and V5 equals. Okay, but I'll state it now. V5 is 9, 3, 7, negative 6. V5 is 9, 3, 7, negative 6. You augment this with the 0 vector. It is all zeros. And you reduce this, which I did. Somebody else did it for me. I got 1, 0, 1 half, 3 halves, 3 halves, 0, 1, negative a half, 3 halves, negative 5 halves, and then 2 rows of zeros. It's augmented with all zeros still. Now, you want to find all the leading ones. In the first row, we have a leading one. Wonderful. In the second row, we have a leading one. In the third row, we do not, and in the fourth row, we do not. So I highlighted all the leading ones. Now, column 1 has a leading one. I don't care which row it's in, but it has a leading one. Column 2 has a leading one. Columns 3, 4, and 5 do not have a leading one. Okay, so you need to go home and study the following. Write down each of their vectors in S, column by column. First, vector 1, V sub 1, first column. V sub 2, second column. V sub 3, V sub 4, V sub 5. Reduce it. Okay? The first two only, it turns out that column 1 and column 2 were the only columns that had a leading one. So, column 1, column 2. You use those two vectors, the ones from column 1 and column 2. If it turned out column 1 and column 3 were the only ones that had leading ones, I would use V1 and V3 as the basis. Okay, so the answer is find a subset of S. Okay, so we'll call it S prime. S prime, which is just vector 1 and vector 2 is a basis for W, which is the span of S. If you're asked to find a subset of S that is a basis for the span of S, all you need to do is write down all the vectors in S as columns, reduce it. Whichever columns have a leading one, you got it. That's it. You have the basis. The first two columns, or coincidentally, column 1 and column 2 had leading ones. They don't have to be in order. It can be columns 3 and column 5. If column 3 and column 5 in the end were the only columns that had leading ones, well then I would say V3 and V5. Over here, V3 and V5 is the basis for the span of S. These two vectors span S, and they're linearly independent. The other three vectors, vectors 3, 4, and 5, are linear combinations of V1 and V2. They're redundant. We don't need V3, V4, and V5. Okay? We can get everything in the span of S just using V1 and V2. Now, just want to make one comment. If I reordered this, that is, maybe I call this vector v4 and this vector v2 and this vector v1. So what do I have? 2, 4, and 1. So I need 3 and 5. This is vector. This is v3, and I'll keep v5 the same. Well, what's going to happen is, if you put v1 first, and v2 second, and v3 third, and v4, and v5, when you reduce it, you might get a different set of vectors. You might get v3 and v5. Okay? It's not going to be unique what you get. You don't have to get v1 and v2. It might be possible that v3 and v5, they span the same set as v1 and v2. That is, they span S. So if S is a spanning set and it's too big, meaning it's not linearly independent, you can remove the dependent ones one by one. Keep removing the dependent ones, and then what you're left with will be a basis. Because if it spans S and it's linearly independent, bingo, it's a basis. Okay, think about this. Stop not understanding the subject. Okay. Now here's a very major theorem. In fact, it's the corollary that's very important. Theorem. If S is, well, let me state what S is. If S equals the set of n vectors, S is v1, v2, up to vn. This is a basis for a vector space V. And, so no period, and T is another set. And T equals W1 through Wm is a linear independent set of vectors in V, then the number of vectors in T must be less than or equal to the number of vectors in S, in the basis. Now we have a corollary. Now, before we go to the corollary, let's look at this theorem again. The vectors, since S is a vector space, then S is linearly independent. Okay? Now, of the linearly independent set of vectors in V. Now, T is also a linearly independent set of vectors in V. But yet, again, S is the basis and T is just linearly independent. Then the number of vectors in the linearly independent set must be no more than the number of vectors in the basis. The number of vectors in the basis is the cap. Linearly independent sets must have either equal to the number of vectors in the vector space or less. Now, corollary. If S equals to V1 through Vm, use a set bracket, and T is equal to, let's use W's, W1 through Wn, are two bases for a vector space V. So we have two bases for a vector space V. The first basis has m vectors, and the second one has n. You know what? M and n must be equal. And the proof is very straightforward using the theorem above. S's are basis for V. Since T is a basis for V, then T is a linearly independent set of vectors in V. So we have T is just a linearly independent set. T is just a linearly independent set of vectors in V. We can say it's a basis, but I just want to say it's linearly independent. And S is a basis. Oh. By the above theorem, the set of vectors, the number of vectors in the linearly independent set T, which is n, must be less than or equal to the number of vectors in the basis S. So now I can reverse this. I can say that T is a basis for V, and since S is a basis for V, then S is a linearly independent set of vectors in V. Similarly, M is less than or equal to N. Hence, M and N are equal. I hate when, in my opinion, when corollaries are more important than the theorem. All bases have the same, all bases for V, for vector space V, have the same number of elements. All bases for V, for vector space V, have the same number of elements. So now we can give this number of elements a name. Let V be a vector space. Well then, what do we call the number of elements in the basis for V? Whatever basis you use, it's going to have the same number of elements as another basis for V. So we can now say the dimension of the vector space V is is the number of vectors in a basis for V. We write the dimension of V to represent the dimension of vector space V. Now, we know that V equaling the set that just has the zero vector is the basis. Oh, so I want to say that V is not just the zero vector. And I also didn't want that line. So V is, the V above is not the zero vector. It's the number of vectors that are required to make up the basis. All bases for V have the same number of elements. Okay, so now, so what about when V is 0? Since the set of the zero vector, since the set that just contains the zero vector is a linearly independent set. Now, why is that true? Because I can take a linear combination of vectors in this set. There's only one vector in that set. I can take a linear combination and get the zero vector, and not all my scalars are 0. Why did I pick 3? Because it wasn't 0. I could have picked 13. Okay, since 0 is a linearly independent set, we say that so there's really no basis for this set. There's no basis for that set. So we'll say that the dimension of the set that just contains the zero vector is, oops, not the zero vector, but the real number 0. So there is no basis for the set of vectors that just has the zero vector. It doesn't have 7 or 8 different vectors. It just has the zero vector. And we're going to say the dimension of that zero vector is 0. We can't say that it's 1 because there's not one vector per basis. There is no basis for that vector space. The set or vector, the V equaling just the zero vector is a vector space. So we have to be able to say what the basis is. What's the basis? Nothing. 0. So some immediate results will be the following. The dimension of Rn, well, Rn, a basis for Rn. One basis is E1, E2, up to En. Oh, and this is n of them. 1, 2, 3, 4, 5, all the way up to n. This set is a basis for Rn, for the vector space Rn. And since there's n vectors that make up the basis, then the dimension of Rn is n. The dimension of P sub n. Well, a basis, remember, P sub n is the set of all polynomials of the degree n or lower. Well, a basis will be 1t squared all the way up to t sub n. This is our basis for p sub n. I can write any polynomial of degree n or less using those vectors, those polynomials. And there are n plus 1 of them. Call this the first one because I want to call it the first because the power is 1. Let's call this one the second one because the power is 2. Let's call this the nth element of the basis because the power is 1. So I used up all of these and is n of them. Let's not forget that one. N plus 1. N plus 1. Dimension of p sub n is n plus 1. Now here's another theorem that's important to know. To be honest, all these theorems are important to know. Theorem. If S is a linearly independent set of vectors in a finite dimensional vector space. That is, the dimension of the vector space V is not infinity. P, not P1 or P2 or P23. This has it's a vector space and it's not finite dimensional because the basis for, or a basis for P is 1t squared t cubed. Remember, P is the set of all polynomials of any degree. So, I'm not going to stop at P50 or Pn. It's going to go forever. This is infinite dimensions. The dimension of P is infinity. Well, we're saying that S is a linearly independent set of vectors in a finite dimensional vector space V. It's not infinite. Then there exists a basis T for V which contains S. In other words, if S is equal to V1, Vn, and Vi is in V. Each of these are in V. Is a linearly independent set of vectors in V. But it's not a basis. Okay? It's not a basis. For example, if S is equal to 1, 0, this is linearly independent in R2, but it's not a basis. It needs another vector. It needs the vector 2, 3. It doesn't have to be the vector 0, 1. There's not just one vector space for there's not just one basis for R2. There's many. Any two vectors in R2 that are linearly independent will span R2, will be a basis for R2. Any three linearly independent vectors in R3 form a basis. Okay, so what we're saying is you can take T, keep these n vectors, linearly independent vectors, add some others, this is a basis for V. Okay. You can add others. That's what it's saying. You can take this set and add something else to it. Add other vectors to it, and then it will be a basis for R2. If S is already a basis for R2, that is, it's linearly independent and it spans, well then yeah, S is still a subset of T. Okay, he just says that the basis T contains S. Well, that means S is a subset of T. It never says S couldn't equal T. It never said S couldn't equal T. S will not be bigger than T, but it certainly can equal. Either it will be, S will be a proper subset of T, or maybe S will equal T. But you can always add more if needed. You can always add more to S to get a basis. If S is linearly independent, you can always add more to S to get a basis. If we're talking about a finite dimensional vector space. Okay, so let's try this. Let's a numerical example. Let V1 equal to 1, 0, 1, 0, and V2 equal negative 1, 1, negative 1, 0. And they're independent. They're linearly independent. In R4, we want, see how I'm going to state this. We want to find our basis for R4 that contains V1 and V2. Now, for that to be true, then V1 and V2 have to be independent. Because if T is a basis, it's going to have V1, V2, and some other vectors. W1, W2, up to Wm. Maybe that's a basis. Well, it can't be if these are dependent, because then the whole thing is dependent. V1 and V2 are independent if, say, C1, V1 plus C2, V2 equals a 0 vector, and not all CI's are 0. So, C1, V1 plus C2, V2 plus 0 for the W's this still just equals to C1V1 plus C2V2, which what I added on is just a zero vector, but I don't really care about that. This equals to the zero vector, and not all this constants or scalars are zero. A lot of them are, but at least one of those are not. So how do you do this? How do you find the basis for R4 that contains these two? Solution. Let S equal to V1, V2, and then a known basis for R4. How about E1, E2, E3, and E4? Remember, E1 is 1 and then 3 zeros. E2 has the 1 in the second position. E3 has the 1 in the third position. And E4 has the 1 in the last position. E4 is 0, 0, 0, 1. Now, what I want to do is remove dependent vectors, but not V1 and V2. I want to remove dependent vectors. So what I do is, like we did earlier, you write down each of these vectors as a column. And if I put V1 and V2 first, they will be the last ones to leave. By the design of Gauss-Jordan elimination, it's going, these two columns, if they're linearly independent, they'll be the last, they won't leave. They won't leave. So we want to reduce this. Now, the first thing is to get that to be a 0. And then the next thing is get what's above and below this one to be 0. So we're setting up for those two to stay. Now, if you work this one out, what you get is the following. You get 1 with all zeros, and then 0, 1, and double 0. And you get 1 with all zeros, and then 11 with a couple of zeros, and 0, 0, 1, 0, and 0, 0, 0, 1. This is what you get. Okay? And now it all comes together. Which are the rows that have a leading 1? First of all, make sure that you agree that this matrix is in reduced row echelon form. Row 1 has a leading 1. Row 2 has a leading 1. Row 3 has a leading 1. And row 4 has a leading 1. Okay? Column 1 has a leading 1. It's right there. Column 2 has a leading 1. It's right there. Column 5 has a leading 1. And finally, it's not in row 5. And column 6 has a leading 1. And remember, the columns were vector 1, vector 2, E1, E2, E3, and E4. So let S prime be the set of vectors that have a leading 1. V1 in this column. V1, V2, E3, and E4. V1, V2, E3, E4 is a basis for R4. And it includes V1 and V2. So we have to assume, or I have to assume, that you know how to reduce a matrix. So now this is very routine work. You want a basis for R4 that has these two vectors, V1 and V2. Now append to it a known basis for R4. I mean, if you just did an earlier, if the last problem you did gave you another basis for R4, you can use those 4 vectors. I don't care which 4 vectors you use. Of course, when it comes to reducing, I rather use vectors that have a lot of zeros in them. But you take in the front, you put the vectors that you want in the basis. And then you append to it a known basis. E1, E2, E3, E4. So here I put V1 as a column, V2 as a column, E1, E2, E3, and apparently I left out the last one, sorry. E4, let's put it in black. 0, 0, 0, 1, that's E4. If you were to reduce this, and again, please put the vectors you want at the beginning. When you reduce it, you will keep those 2 vectors. And keeping means that columns had a leading 1. And you'll get some other columns that have a leading 1. V1, V2, E3, and E4 are the headings of the columns, and they all have leading 1s. That is your basis for R4. So S prime equals that is the basis for R4 and contains V1 and V2. So I did what I needed to do. Let's state another theorem. There's no magic here in this theorem. If you understand what we've been doing, it's going to be very logical. Theorem. Let V be an n-dimensional vector space. That is, the dimension of V is n. And let S equal V1 n be a set of vectors in n. Well, a set of n vectors. A set of n vectors in vector space. If S is linearly independent. Now, let's think about what I'm going to say after. Then, what's true? If V is n-dimensional, then a vector space will, for V, will have n vectors and they're linearly independent. If S is linearly independent and S has n vectors, then S is a basis for V. If S spans V, S spans V, then what can we say? Well, we know a couple of things. If S spans V, well, S spans V, and it has exactly n vectors. Then S is a basis for V. And S is a linearly independent set. It's nice to say this. If S spans V and S has n vectors, then S is a linearly independent set. They go hand in hand. Okay. On to the theoretical exercises. Okay. Show that if the dimension of the vector space V is n, then any n plus 1 vectors in V are linearly dependent. Okay. Let S equal to V1 through Vn be a basis for V. Okay? Let T have the n plus 1 vectors. T1 up to Tn, Tn plus 1. In fact, let's just say up to Tn plus 1. Let this be any n plus 1 vectors in V. If T prime, which is T1 through Tn, is linearly independent, then T prime is a basis for V. So, Tn plus 1, so since Tn plus 1 is in V, we know that Tn plus 1 is in the span of T prime. Because if this is the basis, then any vector is in the span. So T, which is T1 up to Tn plus 1, is a linearly dependent set in V. Why? Because this vector is a linear combination of these vectors. Now, so that's like the first part. Second part, if T prime equals T1 up to Tn is a linearly dependent set. Now, let's be reasonable. Either this set is linearly independent or it's linearly dependent. There's no two ways around it. It's one or the other. If T prime is that, then T, which has all of these vectors, linearly independent, and one more, is also a linearly dependent set. So no matter what, T is linearly dependent. Okay, so let me just say it. Therefore, T is a linearly dependent set in V. No matter which case I look at, no matter which two cases I look at, T is linearly independent. And for the record, those are the only two cases I should look at. Either that T prime set is independent or dependent. There's no in-betweens. And here's a nice problem. Show that if V1 through Vn is a basis for a vector space V, then C times V1, V2 up to Vn, so we just change the first vector, we multiply it by C, then that is also a basis for V if C is not 0. So I have to show that this set spans V and is linearly independent. Let's do linearly independent. C1 times the first vector, which is C1 V1, plus C2 times the second vector, which is V2, all the way down to Cn times the last vector. We assume that. Assume this. Okay. Now, this is one scalar times V1. This is a scalar times V2, all the way down to one scalar times Vn. Okay? Since V1 through Vn is a linearly independent set, that implies that C1C equals C2, all the way down to equal Cn are 0. That is, all of these are 0. All of these are 0. Maybe what I should have done, just slightly different, just emphasize what's going on. It is C1 times the first vector, which is CV1. But that's the same as C1 times CV1 plus C2V2, all the way down to CNVN, which is 0. Well, all of these are 0. Because it's a linear combination of the vectors v1 through vn. Now, okay. Note C1 times C1 times C equals 0 implies that C1 is 0, and that is because we said C is not 0. C is not 0. So what I discovered was all of these coefficients are 0. C2 is 0, C3 is 0, Cn is 0, and C1 is 0. Since C1 equals C2 equals Cn is 0, that implies that the set of this vector with this vector all the way up to that vector linearly independent. That implies the set CV1, V2 up to Vn is a linearly independent set of vectors in V. Okay, so I just showed that this set here is linearly independent. Now I need to show that it expands. I need to show that that set of vectors expands. And we're going to use the fact that you can multiply by 1 anytime you want. Let little v be in V. Let's just name these S and this one T. Since S is a basis for V, we know that V can be expressed as a linear combination of vectors. So V is C1V1 plus C2V2 all the way up to CNVN for some C1, C2 up to Cn. Okay? But I want to show that V is a linear combination of these vectors. Well, if you do C1 and you divide it by C, and then you multiply it by CV1, the C's cancel, and you get C1V1, just like you're supposed to get. Now you have C2V2 all the way up to CNVN. So V is are a scalar times this vector plus a scalar times that vector all the way down to a scalar times that vector. That is, V is a linear combination of the vectors in T. This scalar times, oh, that's the first vector in T, plus that scalar, oh, times, that's the second vector in V. Oh, that's Cn times the last vector in V. So V is in the spanner T. I didn't use the letter T in the first half, but we showed that T is linearly independent and that T spans the vector space V. Any vector in V is in the span of T. Combining this, we can now say, therefore, T is a basis for vector space V. Couple of more proofs. Let S equal V1, V2, V3 be a basis for a vector space V. Now, we want to show that T, which is W1, W2, W3, is also a basis for V, where W1 is the sum of the vectors in S, W2 is the sum of two vectors in S, and W3 is V3. Maybe I should say and. W3 is V3. So, it shows that T is a basis for V. I have to show linearly independent, and it spans V. So, let's look at a linear combination of vectors in vectors in T, which yield the zero vector. Now, W1 is just V1 plus V2 plus V3 plus C2 times W2, which is V1 plus V2. That's not true, is it? It's V2 plus V3, sorry. Oh, the typo. V2 plus V3 plus C3 times V3. And this still equals to the zero vector. Well, combining this is C1 V1 plus, well, we have a couple of V2s. We have C1 plus C2 V2s. When it comes to V3, we have C1 V3 plus C2 V3 plus C3 V3. And this is zero. But now we have a linear combination of V1, V2, and V3. So the coefficients are zero. C1 is 0. C1 plus C2 is 0. C1 plus C2 plus C3 is 0. Well, if C1 is 0, if that's 0, well then C2 is 0. And if this is 0 and this is 0, C3 is 0. This implies that C1 equals C2 equals C3 is 0. Well, that implies that T is a linearly independent set of vectors in V. Now I need to show that T spans V. Let me show that C spans V. Okay, so let V be in V. Little v be in V. Can we find C1, C2, and C3 such that little v is C1 times W1 plus C2 times W2 plus C3 times W3? Can we find that? Answer is yes or no. Well, I know W1 is V1 plus V2 plus V3 plus C2 times W2 is V2 plus V3 plus C3W3 is C3V3. But this is C1V1 plus C1 plus C2 V2 plus C1 plus C2 plus C3 V3. Now, we know that V is a linear combination of vectors, can be written as a linear combination of vectors in set S. Okay. We know little v is d1 v1 plus d2 v2 plus d3 v3. Okay, so C1 can equal to C1, and C1 plus C2 must equal to D2, and C1 plus C2 plus C3 must equal to D3. So C1 is that. Bringing this over to the other side and calling it D1, C2 is C2 minus D1. And solving for C3, C3 is equal to D3 minus C1, which is D1, minus C2, which is this, minus D2 minus D1, and that one is equal to, well, I think I can just sneak it in. You take away D1 and you take away negative D1, that cancels. This is just D3 minus D2. Okay, now I know that D1, D2, and D3 exist. So C1 is B1, and C2 is B2 minus B1, and C3 is B3 minus B2. So I found what these scalars should be to get V. I found that just what they should be to get V. Okay, so let's just write this up. So T spans S. I meant to say the span of T is V. T spans V. Combining with T is linearly independent, we can now say T is the basis for V. Therefore, T is a basis for the vector space V. T is linearly independent, and T spans V. T is a basis for V. Okay, let us try one more proof, one more theoretical problem. And all I do is I get my hands dirty. I just use the definitions. Nothing advanced at all. Let S equal a set of vectors V1 through V, which are a set of non-zero vectors in a vector space V, such that every vector in V can be written in one and only one way as a linear combination of the vectors in S. Every vector in V can be written as a linear combination of vectors in S in a unique way. In a unique way. Then S is a basis for V. Show that S is the basis for V. Should probably say show that. Okay. So we need to show linearly independent and that it spans V. So let's actually write that. Proof. We must show that S is a linearly independent set and that S spans V. Well, since every vector in V can be written as a linear combination of vectors in S, S spans V. Since I'm not going to write down every one of these words. Okay, since every vector in V, blah, 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 blah. All of this, we have that S spans V. So now we have to show linearly independent. So we need to consider the following. Consider C1V1 all the way down to CNVN equaling the zero vector. The zero vector is in V. That is, this is the only way to write the zero vector using the vectors in S, according to what we said. Every vector in V can be written as a linear combination using those vectors in a unique way. But 0 times V1 plus 0 times V2 all the way down to 0 times Vn is a zero vector. That's always true. But wait a minute. There's only one way to write this. There's only one way to write this. So, by uniqueness, we have C1 equals 0, C2 equals 0, all the way down to Cn equals 0. They all equal 0. Hence, S is a linearly independent set of vectors in V. Well, if S spans V, and if S is linearly independent in V, therefore, S is a basis for V. This completes the section entitled Basis and Dimensions.